structure semantic segmentation. So let me start by getting you into a bit of introduction about structure semantic segmentation. So looking at this image over there, we see there's a certain structural quality of the real world that is being reflected in how every individual prediction for every pixel are interacting with each other. There is a certain structure here. However, if we contrast that with a prediction that can come up with any, let's say, out-of-the-shelf semantic segmentation network, we see that, for example, if we observe there the cow is lacking two of its legs, or parts of his body is freely flying in the blue sky, there is something wrong structurally there. And it's not only limited to such scenes, but also, let's say, for a street scene understanding, for example, divider prediction, let's say for lane keeping, such structures are also quite desirable. And what we see here is, if we follow some of these structure semantic segmentation algorithms or policies, we can pretty much recover the situation that a normal CNN would just give us. So with the advent and success of adversarial training and GANs particularly in the past few years, also they have been heavily investigated to be used for structure semantic segmentation. And the idea is quite simple. So we incorporate a discriminator that has a holistic look into all of the labels together and makes a sanity check whether the formation of those every single prediction together makes sense. And if not, if it is easily able to distinguish, let's say, a fake prediction from the semantic segmentation network from the ones that are real coming from human beings, then it can penalize or give feedback to the segmentation network based on that. And later we showed that if we actually leverage the pairing information between the fake and the real prediction that is normally not leveraged in the normal adversarial training, and also do the optimization in the embedding space, the training becomes more stabilized. And however, with both of the methods in general, maybe in general, the adversarial semantic segmentation, there is a major problem. So to illustrate this for you, I would like to ask you the question. Just imagine you are the discriminator and you are given this probability vector, this just represents single pixel. For example, one of them is 0.88 is soft prediction, 0.88 for being a divider, and 0.12 for being the background. And the other one is, let's say, sharp zeros and ones. And I ask you, which one do you think is coming from a network and which one is from a human being? I guess you really don't need to even look at the whole image and the formation to see how good the structure is. You can easily say this is coming from a human being and this is coming from a network. So such a problem, we call it the value-based discrimination. So if a discriminator is easily able to do a perfect job by just looking at the values of every single pixel prediction without really needing to look at the global formation of those pixels, then it really doesn't need to take that extra step, which is much more difficult, right? So actually then such a discriminator doesn't backpropagate gradients that has structural information to improve the segmenter, and actually it hinders this structure-based improvements. Also, a second problem that is a consequence of this is that our network, or semantic segmentation network, would lose the ability to express the much needed uncertainty information. So it needs to fake to be certain because it's dealing with a discriminator that is so much obsessed with sharp zeros and ones value, right? So just in order to show this, so look at this graph. So in the y-axis, we see the average likelihood of the prediction, and this is an average likelihood over the spatial dimension. And we see that if we train a normal semantic segmentation network, with, let's say, the often used cross-entropy loss, so the network certainty is gradually and slowly increasing as we expect. However, if we turn to adversarial training, the common, let's say, framework that we were just talking about, no matter whether this is LGAN or the regular adversarial training, we see that the network is quickly pushed toward converging its prediction to be zero. And no matter how much ambiguities or uncertainties are there underneath in the input image or in the decision-making process, the network needs to fake to be certain. So this kind of graph now verifies both of the hypotheses I was just talking about. Okay, so let's have a step back and analyze the situation that we are in. So, with adversarial, with conventional adversarial training, we have a discriminator. We have actually a critic that is having a holistic look into the input patterns So potentially can give us a structural information and make sure whatever we've predicted makes sense. However, the problem is an inherent ease of distinction between the real and the fake cases by just looking at the values. However, we already know that if a soft prediction like that we have at hand, we don't really mind that softness, like 0.88 or 0.12 by itself is not a problem, as long as this is a correct prediction. So it seems like we are having all the pieces together to come up with a key idea of this study that we were doing. So we want to have all the good things of different words. So we want to still have this holistic critic that looks at the input image. However, we want to reformulate the task and get away from this problematic fake-real formulation that is very easy to be distinguished into a prediction whether this is a wrong or correct prediction. So how is this actualized? So now we have a critic that we call it the Gambler network, that's looking at the input prediction from the fake image, from the semantic segmentation network, comes up with a dense pixel-wise prediction how likely this Gambler network would think this is a wrong prediction. And how do we enforce the network to do this? By such a loss term, which is a negative of a sum of product. And let's say the way we can see that is, this betting map that is coming out of the Gambler network is used as pixel-wise weights in order to scale up the cross-entropy loss. And because if the Gambler network wants to minimize this loss, it means it needs to maximize this sum. And we know that with sum of products, this would be maximized if the two multiplying terms are highly correlated. So the Gambler network needs to come up with weights or with betting maps that are highly correlated or responsive to where the pixel level loss is going to respond highly. And by involving the Gambler network in an adversarial min-max game with the semantic segmentation network, we ensure that they evolve over time and learn from each other. Okay. So however, there is a pitfall in such formulation. So there is one trivial solution, which is in the case that Gambler infinitely bets everywhere. And that's something we want to avoid because then it wouldn't care about the underlying structure. So it means that we need to impose some notion of a limited budget for the Gambler in order to spend. There are different ways to do that, but the one that we found to be working the best in practice was on spatial normalization over the betting map. Where we make sure that all the betting sums up to a constant number. So, the analogy to a real-world gambler is now completed because the real-world gamblers never have infinite amount of money. So they need to think twice before spending their money. So they need to learn about the patterns of, let's say, something being investment worthy or not worth at all. Okay, so let's see how in practice this would improve the structural quality of the prediction. So again, I want to ask you to think you are the gambler, and you are given this dense prediction from, for example, a unit, which is the case here. And I want to ask you, where would you bet? I guess you even don't need to look at the input image pattern in order to say there is something going wrong there. Structurally, it doesn't look like a real-world thingy. So a prediction of a human being there with such a shape inside the car doesn't seem plausible. So that's a very investment-worthy, let's say, location. Also, if you look at the structure of this tree and the border with the building, we see that it is not smooth enough that we want. Also, it doesn't match really the underlying visual evidence of the input image. Something else that we can notice is that the structure of the cars, especially underneath, they are a bit too blobby. So, the tires are not really standing out. So that's also something else that doesn't look like the general structure of the board. And there are many more noisy